Hi, my name is Adolfo Campos, and today we'll explain the variable G pendulum experiment. First of all, we need to know what exactly is a simple pendulum. A simple pendulum is consisting of two objects. A small mass, here represented by the blue sphere, and a string, which has a specific length. The formula that's important for this experiment is that the period, which is the time it takes the pendulum to complete one cycle of its movement, to repeat itself, is equal to 2 pi times the square root of the length times g, g being the gravitational acceleration. In Earth, it's approximately 9.81 meters per second square. But what is important about this formula is that it makes an assumption. It makes an assumption that the angle theta, which is the angle it makes the pendulum with this perpendicular, is approximately equal to sine of theta. This approximation only holds up when the theta is small enough. Usually it's around 10 degrees. Okay, so here you can see a simple pendulum with that has two forces, the tension and the gravitational force. The gravitational force here is mass times the gravitational acceleration. This is equal to the gravitational force. Now, if we expand this free body diagram, we can see this this image. Gravitational force can be divided into two factors. It's cosine and it's sine compared to theta. Now, what's important here is that sine of theta is the restoring force, is what makes the pendulum repeat its movement. Why? Because it goes in the opposite direction of the movement of the pendulum at all times. Here you can see it's going right and the force is going left. So the real formula will be negative as it goes in the opposite direction of the movement. Now we can also calculate the torque of this restoring force using the formula for torque, which includes the distance and the force. Replacing these values with the pendulum, as you can see this arrow represents the restoring force, we will get a torque. It's equal to minus the length here being this distance. As you can see, it says between the pivot and the active point. Here is the pivot, the mass is the acting point, minus length times the force of gravity times sine of theta, which is, as we saw, the restoring force. Now, torque can also be explained as inertia times angular acceleration. So if we combine both formulas and do some rearranging, we get this formula. Angular acceleration is equal to minus m the mass times g the angular acceleration. Remember, this is equal to the force of gravity times length divided by inertia times sine of theta. Here we can use the approximation I told you earlier. The sine of theta is when theta is small enough, approximately equal to theta. So the formula turns into this. Now, angular acceleration is equal to minus the angular velocity squared times theta. So we can replace the formula to get the formula here. But also, the period is equal to 2 pi times the angular velocity. So with the right rearranging, we can get the formula that period is equal to 2 pi times the square root of the inertia divided by mass times g times the length. Now, in a simple pendulum, we know the inertia is equal to mass times the length squared. So if we replace this in the formula, we get that period is equal to 2 times the square root of length divided by g, which is the formula I showed you earlier. Remember, this is with the assumption that theta is small enough. Now, that's the case for a simple pendulum. But in what we're interested in is the physical pendulum. The main difference is that it's a complex object. It's not just a small sphere or a point mass. What's important here is that the length it's replaced by h, which is the distance between the pivot point, here represented by O, and the center of the mass, which is represented by c. Now, as we saw, the formula for the simple pendulum is this one, but for the physical pendulum, it cannot be the same, as the inertia is not exactly the same as a simple pendulum. No? So we need to go back. And the length, as I told you, is replaced by h. Now, what's interesting here is that they are very similar. In fact, if we equal them, we see that the length is equal to the inertia divided by its mass times h. And as we can see, both inertia, mass, and h are constants. So therefore, this is like an effective length for the physical pendulum. It can be considered the length. So we replace this into the formula with the following formula. Now, for the experiment, we need to talk about another concept. Here we have a simple pendulum, and what's important is that we can see its full extent. We can say that the angle of oscillation, the plane of oscillation, here is going left to right, is exactly parallel to our screen. Now we can say that here the angle to the screen is equal to 0 degrees. Now we can also see a pendulum from the side, like for example in here. Now in here it's the angle of oscillation is not exactly parallel to the screen. You can think about it going out and inside the screen a little bit. So here the angle is different from 0 degrees. Now what this implies is that this formula that only functions when the angle to the screen is 0, it has to change. How it changes is we also include cosine of theta. Here theta is actually alpha that I made here. Do not confuse it with theta, which is the angle to the parallel. Now, to explain this, we need to see again the free body diagram of a simple pendulum. This effect also applies to a physical pendulum, as you will see. Here, the restoring force is force of gravity times sine of theta. But when alpha is 0, the extent of the pendulum, the amplitude it gets, it's larger than if it's different from 0. As it is not exactly parallel, from our perspective it looks like it moves less. So therefore this can be assumed that the restoring force is less. It's not exactly force of gravity times sine of theta. Here we need to consider that force of gravity cosine of theta, which is directly downwards from the length of the pendulum, when alpha is 0, here we can replace this g. It's actually force of gravity. Well, it's exactly gravity. The acceleration, the gravitational acceleration, times cosine of alpha. But as here, alpha is 0, cosine of alpha is exactly 1, so we can just use g. But when it's not parallel, we cannot simply eliminate cosine of alpha. Here we have to replace it in the formula. Now, from now on, we will talk alpha as if it was theta. Okay, so for the experiment, what we did was use this machine, which records the period and the angle to the screen of the pendulum. No? For example, here you can see it's set up to 40 degrees. Now, what we're trying to do is to see if the previous formula, the one of this one, when it's not exactly parallel, it's accurate. So what we recorded is what happens at 0 degrees, 10 degrees, etc., up the way to 60 degrees. So here are the results. First we have the degrees. Here we have what can be thought of as alpha in degrees, and here in radians. So we did 5 tries for each angle, and we got some results, and here are their average. This one with their errors, of course. Now, if we use this formula here, remember that we say that effective length is a constant, because all of their components are constants. So if we replace here the period and theta, which remember here is the angle to the screen, we use the ones we got from when the degrees are 0, this column here, we get this effective length. And remember, theoretically it's constant, so we can use this on all the other on all the other angles. We can replace effective length by this number and simply get what will be the what will be the theoretical period. So therefore we have two periods, the one we got experimentally here in these columns and the one we got theoretically, and we can compare these two to see how well it holds up the formula right here. So if we plot them each in one axis, we get this plot with this best fit line. As you can see here in the formula for the best fit line, this number is not 1. If this was perfect, if the theoretical period will be equal to the average period, it will be 1, but here it isn't, and this number here is the error, and as you can see, it does not cover for 1, for a relation of 1 to 1, so therefore it's not exactly accurate. As you can see here, the points at the start are much closer to the best fit line than the ones at the end. And the ones at the end, the ones at higher degrees, are actually the ones causing the most error here. Now, why is this? Why it doesn't agree completely? It's because of the angles, of the more extreme angles. So you can see here, for example, take 10 degrees. What the average period was 1.0827, and what the theoretical period was 1.80877. Here you can see it differs by only 0.005. They are extremely close. But for 60 degrees, the average was 1.45, and the theoretical was 1.5265. Here it differs by 0.1. It's larger than the difference for 10 degrees. Now, why is this? Remember that the formula we used implied that sine of theta is approximately equal at theta. But remember, this only applies for angles small enough, around 10 degrees or less. So when you go above 10 degrees, the error starts to pile up. So this is why at large angles there is a problem, why it doesn't fit exactly with the experiments. Now, for another question, what will the period be if the pendulum had been inclined to 90 degrees? This inclination is, remember, the one to the screen. What value of g does this correspond to? Well, it's easy to see this by using the formula. Here we simply need to replace theta with 90 degrees. Now, cosine of 90 degrees is 0. So therefore this denominator will be 0, which is a problem. As you know, we cannot divide by 0. So therefore the only sensible option is that there is no corresponding period, and therefore there is no corresponding gravitational acceleration. There is not an answer. They not exist. They are not a value. Why is this? Well, we can remember what theta means. Remember when we see this a simple pendulum from the front, from parallel to the screen, here it's 0 degrees. But if we look it from the side, which will be 90 degrees, we are here, we will see something like this. In reality, it will look, because of the third dimension, that it's going up and down a little bit, but what we care here is the left and right movement. And from 90 degrees, there is no movement. And if there is no movement, there is no corresponding period, and therefore there is no corresponding gravitational acceleration. There simply is none, because we cannot have a value if it's not moving. So therefore, what value of g does this correspond to? Well, you could say infinite, but the better option is to say that it's simply there is no value. There's no value of g that corresponds to. Why? Because there's no movement. Okay, now, in order to obtain the same period measurements on the moon, will the pendulum have to be longer or shorter? Well, first of all, we have to see what's the gravitational acceleration difference. Because the Earth is much more massive than the moon, here, as you can see, the gravitational acceleration is much larger. So what does this mean for our formula? Well, we actually, to see it easier, what would it happen, we need to see this other version of formula, where the effective length is replaced by inertia times mass times h. Here g, remember, it should be g times the cosine of theta. But for this thought experiment, we will assume that theta is 0. Okay, so how much longer or shorter it must be? Well, if you remember, a physical pendulum is an object, and h is defined by the length between the pivot point and the center of mass. This here is h. So what it means to have a longer or shorter pendulum is that h changes. Shorter means that h is smaller, larger means that h is larger. So when we have this formula, we assume that everything is constant, both the period, because we have the same period, the inertia, 2 pi, the mass. There only are two variables that change, g and h. And as we know, g is reduced, so g goes down. So in order to counteract this, as g and h are directly proportional, h has to go up. H has to be larger to counteract the lesser gravity. So therefore, this means that the pendulum as a whole has to be longer as h gets larger. So in conclusion, as we saw, the formula for that we saw all this time, it's not really accurate for angles above 10 degrees. If you want to use it, take into account that the angle has to be small. It cannot represent an accurate result if you go above 10 degrees. But if you go smaller, it's actually a very useful formula, as we don't have to rely on the sign of the angle, and we can approximate a lot of values. Well, thank you for listening.